Welcome to this deep dive, where we take fascinating source material and unpack it for you.
Indeed.
Today, we're looking at how we figure out how stars are moving in space, specifically zeroing in on measuring their speed directly towards or away from us.
Yeah, that radial velocity piece.
You might think we could just watch if they get bigger or smaller, but the universe isn't quite that straightforward, is it?
Not at all.
While we can see their movement across our line of sight, what we call proper motion, pinning down that third dimension of velocity, the radial velocity, well, that's been a real puzzle for a long time.
That's right. And knowing the radial velocity is absolutely fundamental. It completes the picture of a star's movement in 3 dimensions.
Right.
Without it, our understanding of how star clusters hold together, how a galaxy rotates, even the behavior of individual stars and, any companions they might have is really, well, it's incomplete.
It's like trying to understand the full story of a storm just by seeing the clouds move across the sky. You miss the crucial information about whether it's also raining or hailing.
Exactly. You need that depth.
Exactly. So our mission today is to explore how the incredible Gaia mission tackled this challenge on a massive scale.
A huge scale.
We're diving into an insightful essay that discusses how they plan to measure radial velocities, focusing on the really clever decision of which wavelength of light to observe.
Ah, the wavelength choice. Crucial.
This is a behind-the-scenes look at a major space mission and the ingenious problem-solving involved.
Okay, let's unpack this.
Yeah, let's
Yeah.
do it. And to really appreciate how big a step forward Gaia was, let's look at some historical context first.
Bad idea.
When the Hipparcos catalog came out in 1997, that was a major achievement in measuring star positions, remember?
Oh, yeah, huge for its time.
It had data on 120,000 stars. But, and this is the key thing, we only knew the radial velocities for about 20,000 of them.
Wow, only 20,000 out of 120,000.
Yeah, a tiny fraction of the picture. That really highlights the challenge. And while ground-based surveys like Corvel and later larger projects like the Sloan Digital Sky Survey Segway and the Radial Velocity Experiment, or RV, they made significant contributions, measuring radial velocities for thousands, maybe hundreds of thousands of stars.
They did. And interestingly, even RV, which observed nearly 500,000 stars in the southern sky between 2004 and 2013, was partly driven by the anticipation of Gaia coming along.
Ah, okay. Paving the way, sort of.
Exactly. These ground-based efforts were crucial stepping stones. But Gaia's ambitions for the sheer number of stars were just on a completely different level.
Right.
And as we've already touched on, the core reason for this huge effort was to finally get that third component of a star's movement through space, absolutely vital for detailed studies of how things move within galaxies.
So with this massive goal of measuring radial velocities for potentially billions of stars, the next big question was, how do you even begin to do that?
Hey, yeah, good question.
The essay points out that trying to get these measurements from telescopes on Earth for so many stars was quickly seen as, well, impractical.
Absolutely. The sheer logistical headache and enormous cost of trying to coordinate so many ground-based observations repeatedly, it would have been, well, astronomical, frankly.
Makes sense.
Plus, there's a major scientific advantage to getting multiple radial velocity measurements for the same star.
Okay.
This lets us study stars orbiting each other, find unseen companions like exoplanets, and get a much clearer idea of a star's real path through the galaxy, though even a single high-quality radial velocity measurement is incredibly valuable information.
And it wasn't just about the practicalities on Earth, was it? The essay emphasizes that observing from space itself offers inherent advantages when it comes to accuracy.
Precisely. The absence of atmospheric scintillation, that twinkling effect.
Right, makes stars twinkle.
That means we get much cleaner data. Plus, being in space allows for much tighter control over any systematic errors in the measurements, little instrumental drifts and things.
Oh, okay.
So the decision to measure radial velocities directly from the Gaia spacecraft itself was a really fundamental one.
Okay, so the where was settled. Space. Now, for the really clever bit. The how, specifically, which part of the light spectrum should Gaia focus on to measure these radial velocities?
Yes.
The essay highlights a detailed study done during Gaia's planning phase with key contributions from Ulysses Munari.
Yes, this was a make-or-break decision. They couldn't just look at any wavelength of light.
Right.
The essay points out that most of the stars Gaia would observe are either intrinsically red or they appear redder because of dust between the stars blocking the bluer light. Interstellar reddening.
Okay, so going for red seemed logical.
Generally, yeah. So focusing on the red part of the spectrum generally made sense. you look where the light is.
That makes intuitive sense. You want to look where the light is most plentiful. But it's not just about brightness, is it? The essay also mentions the need for strong, saturated spectral lines. Let's dig into that. Why are strong lines so important for measuring radial velocity, particularly for fainter stars or stars that don't have many heavy elements?
Right. A key aspect here is that these strong, saturated lines give us a very clear, very reliable signal.
Okay.
Think of saturated spectral lines as being so strong they appear almost black in the spectrum. That makes even small shifts due to a star's motion easier to detect.
Ah, because the contrast is higher.
Pretty much. When a star moves towards or away from us, the wavelengths of these lines shift very slightly, the Doppler effect, right?
Like the siren passing you.
Exactly that effect.
Yeah.
Strong lines allow us to measure this tiny shift even if we don't have a huge amount of light from a faint star, or, as you said, if the star is metal poor, meaning it doesn't have many heavy elements which tend to produce weaker spectral features overall.
Got it.
And also, broader lines can be accurately measured even with moderate spectral resolution. You don't need to see every tiny wiggle in the line to measure its overall shift.
Okay, that makes sense. So the essay then looks at several possible spectral features they considered. Let's start with the potassium, the Ki doublet, around 768 nanometers. What were the pros and cons there?
Well, the potassium doublet had decent strength, which was, a good starting point.
But.
Its strength also changes in a complex way depending on how luminous the star is. That makes interpretation trickier.
Okay.
And crucially, these lines are also known to be produced by interstellar gas clouds. So the light from distant stars could be altered on its way to us.
Ah, contaminating the signal from the star itself?
Exactly. Potentially messing up our radial velocity measurements.
Yeah.
And to top it off, this doublet sits right within a strong band of titanium oxide absorption.
PO.
Yeah, TiO, which is very prominent in cooler, redder stars. So it's hard to isolate the potassium lines in those specific stars.
Right.
And finally, hot blue stars just don't show these potassium lines at all. So it wouldn't have worked across the board.
So, yeah, not the ideal candidate then. Next up was the sodium, the Nachai doublet, around 819.4 nanometers. This was described as being even stronger than potassium. So why wasn't this the winner?
Well, while the sodium doublet is indeed stronger, it had its own set of problems. Like potassium, its strength depends on the star's luminosity, and actually it's weak in giant stars, which are a significant chunk of the galaxy.
Okay, another complication.
And the two lines in this doublet are also extremely close together in wavelength, only about 0.2 nanometers apart.
Tiny gap.
Tiny. This means you'd need a very high-resolution instrument to separate them properly, adding significant complexity and cost to the design.
Right.
Plus, it also gets mixed up with those troublesome titanium oxide bands, and again, these lines aren't present in the hotter early type stars. So, while stronger, it just wasn't a universally reliable option either.
Okay, so we've seen why potassium and sodium weren't the top choices. That brings us to the winner, the calcium second, or Cassiasu infrared triplet, around 860 nanometers.
Yes.
The essay makes a pretty strong case for this. What made it the best option?
This is where it gets really interesting. The calcium-2 endocorablet is fantastic because its lines are strong across most types of stars.
Okay.
The essay mentions consistently strong equivalent widths. That's just a measure of the line strength for regular stars from mid-F all the way to late M spectral types, and even stronger in supergent stars.
Wow.
These lines show up in stars as hot as B8 type and become the dominant features in the cooler M stars. And they show a clear link to how bright the star is, intrinsically, its luminosity.
Okay, strong and widespread. What else?
Importantly, these are non-resonant lines. Think of resonant lines as being very eager to absorb specific wavelengths, like in those interstellar clouds we mentioned.
Ah, so less susceptible to that contamination.
Exactly. Non-resonant lines are less prone to this external influence, giving us a cleaner signal directly from the star. And because they are so strong, we can get accurate radial velocities, even from relatively faint stars, using a technique called cross-correlation.
Okay, what's cross-correlation,
Yeah.
briefly?
It's basically comparing the observed spectrum, with all its noise, against a known template spectrum to precisely measure the overall shift, even if the individual lines aren't perfectly clear.
Got it. So robust, even with weaker signals.
Very robust.
That sounds like a much more versatile choice. But there's another really clever point mentioned. The presence of the Passion series of hydrogen lines in hot, early type stars within the same spectral region. That sounds like getting two for the price of one.
Exactly. This was a real stroke of genius, you could say.
Uh-huh.
In those hot early type stars, early F stars, Where the calcium-2 lines are weak or even absent, the Paschen series of hydrogen lines steps in. These lines are also strong in those stars and allow us to measure radial velocities perfectly well.
Brilliant.
What's more, these hydrogen lines are also very useful for classifying these types of stars. So, by picking this specific part of the spectrum, Gaia could effectively measure radial velocities for an incredibly wide range of star types, from the hottest blue giants down to the coolest red dwarfs. One instrument setting covers almost everything.
That is really clever. And the advantages don't stop there, do they? The essay mentions that this spectral region, around 860 nanometers, has the added bonus of being free from telluric absorption lines.
That's right. Telluric lines are absorption caused by molecules in Earth's own atmosphere. Water vapor, oxygen.
Ah, so they don't interfere.
Exactly. This is a significant practical benefit. It means that if astronomers needed to do follow-up observations from ground-based telescopes, the data wouldn't be contaminated or complicated by our own atmosphere, allowing for consistent and comparable measurements between space and ground.
Very useful for verification and deeper studies.
Yeah.
Okay, so beyond just getting radial velocities, it seems this choice of spectral region also unlocked some unexpected scientific bonuses. The essay mentions the presence of several other metallic lines.
It did. Interestingly, yeah, within this same small window of the spectrum, there are lines from elements like nitrogen, silicon, magnesium, titanium, and even helium for the hotter stars.
So what can you do with those?
For brighter stars where the signal is good, the relative strengths of these lines can be used to perform detailed chemical analysis, essentially figuring out what the star is made of, its metallicity and abundance patterns, and you can get even more precise spectral classifications.
So it wasn't just about motion, it was also about understanding the fundamental properties, the chemistry of these stars.
Absolutely. More bang for your buck, scientifically speaking.
And it could even help us discover unusual stars, right? The essay gives examples like P Cygni stars, B stars, T Tauri stars.
Exactly. Stars with unusual characteristics often show distinctive shapes or extra emission features in their spectral lines.
Okay.
The KD's-2 triplet region, along with the Paschen and helium lines present there, is sensitive to these peculiarities. So it makes it easier to identify and study these fascinating objects, whether it's, the material being ejected from a P Cygni star, the disks around B stars, or the intense activity of young T Tauri stars showing emission in calcium.
Adds another layer of discovery potential. Finally, the essay touches on a somewhat unexpected benefit: the presence of a diffuse interstellar band, or DIB, at 862 nanometers.
Yes, these DIBs are still a bit of a mystery. We're not entirely sure what molecules or dust grains cause these broad, shallow absorption features in the light from distant stars.
Right, they come from the stuff between the stars.
Exactly. But the DIB near the Casta triplet, while not very strong, seems to be linked to the amount of dust and gas between us and those stars, what we call interstellar reddening or extinction.
So how is that useful?
It means that by studying this faint band across millions of stars, Gaia could potentially contribute to creating much more detailed 3D maps of the dust that lies between the stars, particularly in regions where there's a lot of obscuring material, understanding the interstellar medium better.
That's a fantastic bonus outcome. It's incredible how much information can be packed into such a small slice of the light spectrum. The essay even includes example spectra showing how the Casta triplet region changes with temperature and the amount of heavy elements in a star. It really makes the science tangible.
It does. Those spectra really illustrate the power of the choice. And as the essay briefly mentions, future discussions could delve into the specifics of the radial velocity spectrometer instrument itself on Gaia, the really complex data processing needed to extract these velocities accurately.
Oh, I bet that's a whole story in itself.
Oh, yeah. And, of course, the incredible wealth of scientific discoveries that these, over 33 million radial velocity measurements in data release 3. But they're now making possible.
33 million, just staggering compared to the 20,000 from the Hipparcos era.
Night and day.
It's clear that those early decisions, especially the choice of this spectral region, were absolutely fundamental to the success of Gaia's radial velocity program. And the essay rightly gives credit to Ulisse Minori for his key role in proposing and demonstrating the value of this particular approach.
Absolutely. What's fascinating here, I think, is how his seemingly simple question, what wavelengths should we look at,
Right.
led to this whole series of incredibly careful, thought-out choices. Driven by the need for reliable measurements across a huge variety of stars, the advantages of being in space, and then finding all this exciting potential for a broad range of additional scientific discoveries packed in there too.
Yeah.
This wasn't just about measuring how fast stars are moving. It was about unlocking a much deeper understanding of the stars themselves and the galaxy they live in.
So, to wrap things up, this deep dive has shown us that the selection of the calcium-2 infrared triplet for Gaia's radial velocity measurements was a crucial turning point in the mission's design. It wasn't a straightforward choice, but a carefully considered decision based on the strengths and weaknesses of different parts of the spectrum, the characteristics of the stars being observed, and the goal of maximizing the scientific information gained. This single decision paved the way for an unprecedented catalog of stellar motions.
And if we connect this to the bigger picture, it really highlights how incredibly detailed the planning of a major scientific mission like Gaia is. Every technical decision, even something that might seem quite specific like the choice of wavelength,
Right.
it has these far-reaching consequences for the kind and quality of data we can collect and ultimately for our understanding of the universe.
This raises an important question for you, our listener. Think about how seemingly technical decisions in large scientific projects can have such profound and wide-ranging impacts on our knowledge of the universe.
Hmm.
What other hidden layers of complexity might exist in the data we receive from space, just waiting to be uncovered by equally clever and insightful analysis? It's definitely something to ponder. Thanks for joining us on this deep dive.